It feels like you can't go 5 minutes these days without hearing about it. It is the background radiation of our entire lives right now. It's writing emails, it's generating those weird images of the Pope in a puffer jacket. It's seemingly everywhere.
It's the defining buzzword of the decade, without a doubt.
Exactly. AI, artificial intelligence. But here's the thing that bugs me, and I think it bugs a lot of people. If you actually stop someone on the street, or even someone pretty tech savvy, and say, okay, cool, but define AI for me. What actually is it?
You get a lot of blank scares.
You do. The conversation just falls apart. You get, oh, well, it's machine learning, or it's when computers get smart, or my personal favorite is the thing that's going to take my job. But practically no one can explain the underlying logic.
Well, that's because we usually confuse the product with the process. We see the chatbot or we see the recommendation algorithm, but we don't see the architecture underneath.
So today, we are going to fix that. We are going to skip the hype, skip the stock prices, and do a deep dive into the actual brains of the operation. We've got a stack of lecture notes and slides here from a university-level course, specifically Introduction to Artificial Intelligence from California State University, Channel Islands.
And this is excellent source material because it really strips away all the marketing fluff. We aren't talking about sci-fi scenarios here. We are looking at the foundational concepts that computer scientists actually use to build these systems.
We're going to cover the Turing test, a framework called PEAS that engineers use to build self-driving cars, and why, and this is a teaser for later, it is mathematically harder for a robot to fold a laundry towel than it is to play grandmaster-level chess.
That is one of my favorite facts in the entire field. It's so counterintuitive.
It is. But the central question we're trying to answer today is deceptively simple. Is the goal of AI to build a brain that thinks exactly like a human, or is it to build something else entirely?
And the answer to that question basically explains everything about why modern AI works the way it does. It explains the strengths and it explains the weird limitations.
So let's get into the source material. The lecture starts by throwing a curveball. It says there isn't actually one single definition of AI.
No, there isn't. Not really. If you look at the history of the field, there's been this massive split, almost like a schism. The lecture notes break it down into 4 distinct definitions organized into 2 camps. On one side, you have the human approach.
Okay.
And on the other side, you have the rational approach.
Human versus rational. Let's start with the human side. This feels like the movie version. We want to build a machine that's basically us, but made of metal and sapana.
Right, and the first definition in this camp is thinking humanly. This is really the domain of cognitive science. The idea is, if your definition of AI is a machine that thinks like a person, then you first have to figure out how a person actually thinks.
Which is a nightmare, because I don't think we fully understand that ourselves yet.
Exactly. You're talking about introspection, brain imaging, mapping neurons. You are trying to reverse engineer the biological brain and then code that messiness into a computer. It's a fascinating field, but as a way to build practical software, it's incredibly difficult.
Okay, so if thinking humanly is too abstract, what's the other human option?
The second definition is acting humanly. And this brings us to 1950 and the father of computer science, Alan Turing.
The Turing test, the imitation game.
Precisely. Turing proposed this test because he realized asking, can machines think, is a linguistic trap. It's too philosophical. So he changed the question to something operational.
He changed it to, can a machine fool a human interrogator?
Right. So you're sitting at a computer chatting via text. On the other end, there's a human and a computer. If you can't tell which is which, the computer passes.
Simple enough.
And the source notes that Turing actually made a specific prediction. He thought that by the year 2000, a machine with about 120 megabytes of memory would be able to fool 30% of human judges for 5 minutes.
120 megabytes. I think the picture of my dog on my phone is larger than that. But did we hit that benchmark?
Technically, we're flirting with it now with large language models, but in 2000, not even close. But, and this is more important, the lecture notes point out that the Turing test might actually be a bad test of intelligence.
How so? It sounds intuitive. If it acts like a human.
Because fooling a human isn't the same as intelligence. It's really the art of deception. The source brings up a famous philosophical argument called the Chinese room. This is crucial for understanding why AI researchers shifted away from this.
Okay, I love this thought experiment. Walk us through the Chinese room.
Imagine you are locked in a room. You do not speak a word of Chinese. But you have a massive book of rules, a giant manual. People outside the room slide slips of paper with Chinese characters under the door.
Okay, so I get these symbols I don't recognize.
You look at the paper, you check your rule book, and the book says, if you see squiggle A followed by squiggle B, write down squiggle C. You just copy the shapes and slide the answer back out.
So to the person outside, I seem like I'm fluent in Chinese. I'm answering their question.
Exactly. You are passing the Turing test perfectly. But do you, the person in the room, actually understand Chinese?
No, not at all. I'm just a guy following instructions. I have no idea what I'm saying. I'm just matching patterns.
And that is the critique of the acting humanly approach. You can simulate understanding without having any true understanding. You're focusing on the facade, not the substance.
So if trying to be human forces us into these philosophical traps, what's the alternative? You mentioned the rational approach.
This is where the field really found its footing and became a rigorous science. We move away from psychology and into logic and economics. The third definition is thinking rationally. This goes all the way back to Aristotle.
Syllogisms, right. Socrates is a man, all men are mortal, therefore Socrates is mortal.
Pure logic. The dream in the 60s and 70s was that if we could just teach a computer the laws of formal logic, it should be able to solve any problem in the universe.
But I'm guessing there's a catch, or else we'd have solved the universe by now.
A huge catch. The source points out a huge problem. The real world is messy. It is very, very hard to write a logical proof for, is that a stop sign or a sticker on a billboard?
Right. Or is that person being sarcastic? Logic breaks down when things get ambiguous.
Exactly. Which brings us to the winner. The definition that underpins almost all modern AI, from ChatGPT to the Mars rover. The fourth definition. Acting rationally. This introduces the concept of the rational agent.
Okay, this feels like the core of the deep dive. The rational agent, what actually is it?
A rational agent is simply something that acts to achieve the best expected outcome.
That's it.
That's it. But there's so much power in that simple definition. It doesn't care if it thinks like a brain. It doesn't care if it passes some philosophical test. It cares about utility maximization.
Which is a concept from economics.
Straight from economics. It's calculating. I have a goal. I have information coming in. What action gives me the highest statistical probability of hitting that goal?
So it's not trying to be human, it's just trying to be effective.
Perfectly put. Think about a toaster. If your toaster perfectly toasts your bread every single time without burning it, it is acting rationally. It is maximizing utility.
Okay.
Now, if you built a human AI toaster, it might burn your toast because it was distracted thinking about poetry.
Or it might lie to me and say it toasted the bread when it didn't, just to pass a Turing test.
Exactly. The rational agent approach treats AI as an engineering problem, not a philosophy problem. We aren't trying to build a soul. We're trying to build a machine that makes the best decision.
And this lets us map out the anatomy of an AI in a really specific way.
Right.
The lecture notes have a diagram of this loop, the agent-environment interaction.
It's a cycle.
Yeah.
You have the environment, that's the world.
Yeah.
And you have the agent. The environment sends data to the agent through sensors.
Eyes, ears, cameras, microphones.
Right. The agent processes that data, they're called percepts, and then uses actuators to do something back to the environment.
Actuators, I love that word. It just means the thing that moves, right?
Basically, wheels, screens, speakers, robotic arms, anything that changes the state of the world.
The source uses a specific framework to design these agents, Ps, P-E-A-S.
Yes. If you are an AI engineer, you live by Ps. It stands for performance, environment, actuators, sensors. It's the checklist.
So let's apply this. The source uses the self-driving car as the prime example. Walk us through the Ps of a Tesla.
Okay, start with P performance measure. This is crucial. What are the points the agent is trying to score? For a car, you want safety, speed, legality, and, comfort.
And there's a trade-off there, right? The safest car never moves. The fastest car ignores red lights. The rational decision is balancing those points to get the high score.
Precisely. Now, E environment, that's the road, other cars, pedestrians, weather, all of it.
Actuators.
Steering wheel, accelerator, brakes, signal lights.
And finally, S sensors.
Cameras, LiDAR, radar, GPS, all that data flooding in.
So the car is in this constant loop. Sensor data comes in, I see a red light, the agent calculates. To maximize my performance measure of safety and legality, I need to stop. It sends a command to the actuator, brake.
Exactly. But here is the nuance that makes the rational agent model so powerful. The source mentions bounded rationality.
Bounded meaning limited.
Meaning realistic. In the movies, AI is omniscient. It knows everything. In the real world, AI is limited by computational power and time. It can't simulate every possible future.
Right.
Imagine the self-driving car is driving 40 miles an hour. A kid runs out from behind a parked truck. The sensors pick it up. The computer has maybe 200 milliseconds to make a decision.
It doesn't have time to solve some complex philosophy problem about the value of life.
No. A rational decision doesn't mean the perfect decision. It means the best possible decision, given the information it has and the time it has. If it slams the brakes and saves the kid, but the car behind rear-ends it, that was still the rational decision.
Because it maximized the expected utility based on what it knew at that split second.
Exactly. It separates the quality of the decision from the outcome. You can make a rational bet in poker and still lose the hand. That doesn't mean you played irrationally.
Speaking of poker, that leads us to the next section of the notes, the environment. The source makes a big deal about how the world determines how hard the AI's job is.
Context is absolutely king. The source contrasts two types of environments, deterministic versus stochastic.
That is a great word. Let's define it.
Let's use chess to explain the difference. Chess is a deterministic environment. When you move your pawn, there's zero chance that the wind blows it to a different square.
Right.
The outcome of your action is completely determined by the rules. The board state is fully visible. There are no secrets. This is why AI crushed humans at chess decades ago. It's just math.
Okay, so that's deterministic. Now compare that to driving, or the other example the source gives, stock trading.
Those are stochastic. That
Yeah.
basically just means randomness is involved. You can drive perfectly, but another driver might be texting and swerve into you. You can buy a stock based on perfect logic, and then a natural disaster happens and the market crashes.
So in a stochastic environment, the rational agent isn't dealing in certainties, it's dealing in probabilities.
Yes, it's saying there is an 80% chance this car will stay in its lane, so I will proceed. It's constantly making bets, in a sense.
This explains why we have AIs that can beat the world champion at Go, but we still don't have robots that can reliably navigate a crowded party carrying a tray of drinks.
The cocktail party is too stochastic. It's too chaotic. And this leads to the hierarchy of agents the lecture describes. You have simple ones, like reflex agents.
That's just if X, then do Y.
Right. If the temperature is above 75, turn on the AC. It doesn't plan, it just reacts. But then you move up to goal-based and utility-based agents. They simulate the future. If I turn left, does that get me closer to my goal?
And at the very top of the food chain, the source lists learning agents.
This is the game changer. A learning agent doesn't just act. It has a component called a critic.
A critic.
Yes. It observes its own actions and compares the result to the goal. It basically says, hey, you braked too late there. That was scary. It then updates its own internal rules for next time. It rewrites its own code.
That's the difference between a calculator and something like ChatGPT. The calculator never gets better. The learning agent evolves.
Exactly.
I want to zoom out for a minute to the history section of these notes, because looking at the timeline, it's surprising how long we've been chipping away at this. We tend to think AI was invented, 5 years ago.
It feels that way because it just got very good very fast. But the Hall of Fame in these notes goes back decades.
Yeah, let's talk about games. Games seem to be the proving ground for these rational agents.
They are the perfect petri dish because the rules are clear. The big cultural moment was 1997, IBM's Deep Blue.
Beating Garry Kasparov, the world chess champion.
That was huge. And the source quotes Kasparov saying something really haunting after that match. He said, I could smell a new kind of intelligence across the table.
Smell a new kind of intelligence. That gives me chills. He wasn't playing a calculator. He felt like he was playing a mind.
Even though, technically, he was just playing a very, very fast search algorithm.
Yeah.
But then, look at 2007. The notes say checkers was solved.
Solved sounds so final.
It is final. A team proved that if both sides play perfectly, the game is always a draw. A computer can now literally never lose at checkers. It's mathematically impossible.
That kind of takes the fun out of it. But then we have the boring stuff that is actually way more impressive. Logistics.
The boring stuff runs the world. The source highlights the 1991 Gulf War. The U.S. forces used an AI planning program, a rational agent, to organize logistics for 50,000 vehicles, cargo, and people.
That's incredible. It's less Terminator and more super efficient FedEx.
And NASA. The source mentions the remote agent on Deep Space One in 1999 and MapGen for the Mars rovers. These agents are millions of miles away. You can't joystick them.
Right, because of the time delay. If you see a cliff on the camera and hit stop, the rover fell off that cliff 10 minutes ago.
Exactly. They have to be rational agents. They have to look at a rock, analyze their battery power, and decide, Is it safe to drill this all on their own?
I love the Mars rover example because it fits that rational agent definition perfectly. It's alone on a planet, maximizing the utility of science without falling into a crater.
But here's the twist. We can send a robot to Mars. We can beat the Grandmaster at chess. But the lecture highlights one task that is incredibly hard for robots.
Which is?
Laundry. Specifically, folding a towel.
Wait, really? Folding a towel is the final boss.
In robotics, yes. The source highlights a project on this. A robot designed just to fold a towel.
Why is that harder than calculating a trajectory to Mars?
Think about the environment. A chessboard is rigid. A planet's surface is rigid. A towel is floppy. It's deformable. It has infinite configurations. For a computer to look at a crumpled pile of cloth and understand that is a corner, and then pick it up while it changes shape in real time.
The math must be astronomical.
It is. It's called Moravec's paradox. The hard stuff, like calculus, is easy for AI. The easy stuff, like tying a shoelace or folding a towel, is hard.
That really puts the whole human versus rational debate into perspective. We aren't just trying to clone a brain. If we cloned a human brain, we'd be great at folding towels and bad at calculating logistics for 50,000 trucks.
Right. We are building something with a completely different set of strengths. The slide on synthesis at the end of the lecture really drives this home. It lists all the fields that go into AI: philosophy, math, economics, neuroscience.
It's a total melting pot.
It is. It's economics providing the concept of utility. It's philosophy asking what logic is. It's neuroscience providing the inspiration for the networks. Modern AI isn't just code. It's what happens when you combine all these disciplines.
We stopped trying to make them be us and started making them useful to us.
That's the key shift, from imitation to interaction.
So that brings us to the end of the source material, but I want to circle back to one thing you mentioned earlier, the learning agent.
The one with the internal critic.
Right. You said the learning agent has a critic component that judges its own performance so it can improve. I did that wrong. I should do it differently next time.
Yes. It's an error correction loop.
So here's my question. If an AI creates its own internal critic, a voice inside its code that observes its own behavior and corrects it, at what point does that feedback loop stop looking like math and start looking like introspection?
That is the million-dollar question.
Because that's what consciousness feels like, right? It's me watching myself and judging my own actions.
When the system begins to observe itself, to optimize its utility, the line between advanced algorithm and self-awareness gets very, very blurry. The math hasn't changed, but the emergent behavior looks a lot like a mind at work.
Something to think about the next time your GPS judges you for missing a turn.
Indeed. It's just trying to maximize your utility.
We hope you enjoyed this deep dive into the rational brain of AI. Next time you see a Roomba or a self-driving car, just remember, it's a rational agent, sensing, acting, and trying its best to get the high score in a chaotic world. Just like us, really. Thanks for listening.
See you next time.